All right, good morning. So today we're going to do some review, and I've got the flow chart and some character tables and things to pass out. This is what you're going to get on the exam, so you'll see the same thing again. So you know, I have a bit of a safety net. Before we get into the review, though, I just want to reemphasize. Notice how it's not just character tables; it's character tables and direct product tables. So, just as a very baseline evaluation, look at the two. They, you know, if you just are 6 feet away, they look the same. But if you look closely, notice the character tables have symmetry elements across the top, right? C2 and reflection planes, sigma planes, and so on. The direct product tables are always products of Millikan notations. So A1s times A1s and A2s times B1 and so on. So just so that you recognize the difference, just at a base level of those two different kinds of things. Also notice that the direct product tables rarely have the G's and U's on them. They have the general rules over there on the right that say that there's GU rules too. So if you have A1 times A1, it's A1, but if you have A1G times A1U, then it's A1U, because G times U is U. So you've got to include both of those rules. You use the direct product table to give you the A and the 1 or the B and the 2, but then you use the G or U rules to determine whether it's even or odd. So that's just a little bit of review on those. So what I've done is I've got a PowerPoint here that has all of the homeworks in here. So if you have specific homeworks, we can go through and answer your questions on the homeworks. This test is over homeworks 1 through 3, but on the test there is a problem just like this right here that's on 4, but it's the same material that's on 1 through 3. You see up there those 4 molecules. So that's how it's presented on the exam, is you have 4 molecules like that with A, B, C, or D, and you're asked questions about them. Which one of these is C2V? Which one of these is octahedral? That kind of thing. And you need to be able to know the symmetry or the point group of each of those. And you'll have the flow chart. So like you could go through the flow chart with all 4 of those and mark them and so on. So it's not I know you're a little panicked because I've been gone all week and you've got an exam on Monday, but don't be panicked. It's if you've worked on the homework and you've watched the videos and we're going to have this review session today, I think you'll be prepared. Okay. So with that, let's go to your questions. Okay, you jumped on it, right?
In the first video about the symmetry, that PowerPoint, when you were discussing plotting them and trying to figure out the even and the odd, I just want to understand more. Is it always consistent that the even is going to be both positive? Are we talking about the quadrants? It's kind of what's determining positive or odd or even?
Yeah, so you're talking about odd or even with respect to G and U, inversion?
No, this particular slide.
Okay, sure.
This particular slide.
Yes, okay. So let me just draw on this page right here. So the picture that she showed on this slide, it was the wave functions like this, where you had one like this here, and this is the origin, okay? And this is minus L/2 and L/2. And then there was the ground state one that looked like this, okay, with 0 in the middle. So in all of these cases, and even with molecules, the origin is where you stand in terms, mentally. You stand there and you look to the right and you look at the wave function. And like in this case, let's look at the top one. I'm standing on 0, the origin, and I look to the right and the values, it looks like a little mountain, positive values. And I look to the left and it's the same shape, but it's negative values. Okay, so the right looks like the left except for the sign. So that's odd. Yeah, yeah. If I'm on this one, I'm standing at the origin and I look to the right, it's all positive values and it slopes down like that. I look to the left, it's all positive values, it slopes down like that. That's even because they're mirror images of each other. Yeah. The reason I'm trying to describe it in those kinds of terms is let's take a dz squared orbital. So later on we're going to get into orbitals, and you have this ring around the middle, and you've got a dumbbell on top and a dumbbell on bottom. Okay, and so this ring around the middle is shaded, or it's it's the opposite, whether it's shaded or unshaded with the dumbbells. So if I'm standing on the origin and I look up, I see a positive dumbbell and a negative ring. And I look down and I see a positive dumbbell and a negative ring. It's the same whether I look up or down. That's even on the z-axis. So that's why I'm trying to use analogous language instead of a strict mathematical definition of even and odd. Now, if I were to pick a point up here, like just pick a point on that wave function right there, and I go through the origin and pick a point on the exact opposite side, are they the same sign? Yes. So that's another way to say that it's even. And that's what I was trying to show with those two lines. If I go over here to the right and pick a point, it's negative. If I go the same distance to the left and pick a point, it's positive. So the only difference between those two is the sign in front, but positive or negative one. And so if it's a negative one, it's odd. If it's a positive one, it's even. And you can see that in that pack of notes. So if I go left, pick a point, it's that high, positive. If I go to right, pick a point. I have to go the same distance and go to the function, and they're both the same. So that's even. Yeah. Yeah. And then we need to know that because then when we do the transition dipole moment integral, so this is a bit of review with these two here, we know this is even. So I'm going to use the GU designation. So this is G for even, and this is U for odd. And light is F of X equals X. And so if I plot that, it looks like this. Right, here's 0, here's L over 2, here's minus L over 2. So what's the value of X at L over 2? It's L over 2. So this right here comes up here to positive L over 2. That's what I mean by F of X equals X. It's just the x-axis. It has a positive end and a negative end. So is this an even or odd function down here? So these values are positive, these values are negative. They have the same magnitude. I go over here to the right and pick a point, and then I go the same distance to the left. It's the same magnitude, but opposite sign. So it's an odd function. So this is a U. Right here, U. So if I want to make the transition dipole moment integral, we're going to call this n equals 2, n equals 1. And so if I'm going up to 2, I'm using light, x-polarized light, starting at state 1. We always kind of do it backwards. The lower state or initial state is on the right, the final state's on the left, and x is in the middle, although I'll never count off for that, but it's just the traditional way to do it. So this is a transition from 1 to 2, and we're seeing if it's allowed. Okay, so let's pretend this math is too hard for us to do, because it's an exam and we got to be quick. Okay, so I'm going to substitute the symmetries of all three of those functions. Okay, so I can look at this and I can say wave function 1 is G, light is U, and wave function 2 is U. So I've substituted the symmetries of those functions. So this is a mathematical integral, and to know whether it's 0 or non-zero, all I have to know is the symmetries of those functions. So I can just not do the math and just look at the symmetry. So U times G, if we look at those general rules, is U. Think of these as plus and minus 1. So minus 1 times a plus 1 is a minus 1. And then we bring this one down. Okay, so those are still multiplied by each other. We're still integrating over all space. So -1 times a -1 is +1, or u times u is g. So we have the integral over all space of these three functions multiplied by each other, but the result of that multiplication is an even function. And so when we integrate over all space, the negatives don't cancel the positives, and it becomes non-zero. We don't know which is more strong, whether the negatives are more strong than the positives, but it's not a zero result. It's a non-zero result. And then since we square it, we know that it's a positive probability. But anyway, this is not equal to zero because it's even. Not equal to zero. And so we would say this is allowed.
Is X always U, or we just picked it because that's how you labeled it on that graph on the bottom?
X is always uneven. X is always odd, okay? Now, every character table has a different definition of what odd is, okay? The only even symmetry on the character table, so everybody give me your eyes, the only even symmetry on a character table is the top row. Every other row is odd in some manner. The only even row in a character table is the top row. So that's why I don't want to tie you to G, right? Because some character tables don't have G's and U's, but all character tables have a symmetric result, and that's the top row. Notice the top rows always have +1s. No matter what you do to the function, you're going to get a +1. Whether you rotate it, reflect it, invert it, it's +1 on the top row. All the other rows have some -1s in them. They have some odd nature. If I integrate them over all space, I get 0. Okay. So after I do this triple integral, this integral of three functions multiplied by each other, and I take them pairwise and use the direct product table, and I produce a different symmetry, bring this third one down, multiply them in the direct product table, get a third symmetry, and then I'm integrating over all space of whatever symmetry that is. If that's not in the top row, equals 0. Forbidden. If it is top row, allowed. Okay, so what does this mean, top row? You got to know the character table, which means you got to know the point group, which means you got to know the structure of the molecule, which means you need to know how to draw molecules. Now, I've given you the molecules on the test for this first one, okay? But on the lab, you're drawing your own, like you're practicing drawing the molecules, and so the TAs will grade your lab to see if you drew them correctly and so on. But on the exam, it's 33 questions. I want to run them through the Scantron and get you your grades right away. So there won't be any handwritten on this particular first exam. So you always have some choices at least. Now there's 2 or 3 that have multiple selections, but not all of them have multiple selections. But be confident in your responses. That's the trick, isn't it? Okay, thank you for the question. I think we covered more than you were asking, but yes.
This might be a dumb question, but are we allowed to use model kits during the test or
No,
no?
but mainly, the molecules are given. I want you to notice how I've drawn them very specifically, how those hydrogens are right on top of each other. If you're still drawing them like let's draw this one here, right here. Okay. If this is you, okay, if you're still sort of, I would call it in the freshman level of Lewis dot structures. That's not an insult, but it's going to cause you trouble. If you still draw your structures like this, then you're going to have trouble because I don't see any threefold symmetry in that molecule. It's really hard to see. Those hydrogens, if this is the z-axis right here, this carbon chlorine molecule, so this is the z-axis coming right out of the top. Z. I'm running out of space here. Yeah, z-axis. Okay, the y-axis is coming straight out the side here, and the x-axis is coming straight out of the board. Notice that hydrogen is on the left side of that x-axis. It's pointing off to the right, and those hydrogens should be eclipsed from each other. Like they're one right behind the other. And so you can see how this thing could rotate 1/3 of a turn around the z-axis if you draw it right. Okay. the one on the right that I've drawn, I can't see the rotation axis there because it looks like everything's 90 degrees. I've just drawn a wedge and a dash, but the hydrogens aren't eclipsing each other. So it's important that you do your best to draw the molecules when you're drawing them, like for the lab, with the wedges and dashes to where these hydrogens are very close to each other. Because if you're looking at the molecule in the model kit correctly, you know, you've got one hydrogen going down over there, and these two, if you look at them straight from the side, one's on top of the other from your perspective. Okay, so you need to draw that as accurately as possible so that you see the symmetries and so that you can tell things like the ethane on the right. Notice how this ethane here, one of the TAs tattled on you guys and said you couldn't remember the difference between eclipsed and staggered. Okay, so which one is this? Is this eclipsed or staggered here on D? This ethane. Let's see right here. It's staggered. How do I know that? Well, this hydrogen is in the plane of the paper, and these two hydrogens are out of the plane of the paper. One's going back behind the paper, and the other one's in front of the paper. So they're not on top of that other hydrogen. They're staggered. Okay. So if you don't draw the molecule correctly, it's difficult to see the symmetry. But now that I've drawn those as correctly as you can in 2 dimensions, then you can see things like one is staggered. The one going down is in the plane of the paper, and the two up above are in and out of the paper. So they're not above each other. They're not eclipsed. They're staggered. So let's take that ethane through the flow chart together. Okay? So flip the other page. Here you go. Yes. So we'll just walk through all the questions. Is it linear? No. Good. All right, there's hope. Does the molecule contain 2 or more unique C3 axes? Do we have any C3 axes? I hear a mumble. Don't know. What about that carbon-carbon axis? Yeah, so I have the hydrogen, hydrogen, hydrogen. So I could rotate them a third of a turn into each other. So it has a C3 axis, which is the carbon-carbon axis. Okay, that is also what defines, since it's the highest rotation axis on that molecule, it's the Z-axis. And so we would draw the Z-axis along that carbon-carbon bond. And we put it off to the side just so it doesn't get busy. Okay, but that's the Z-axis, that's the principal symmetry axis. It's also the C3 axis. So all 3 of those are the same thing, going up and down. And then we have this 3-fold rotation that goes around with the hydrogens. Okay, so we would say, does it have more than one? No, there aren't any other C3 axes going through this molecule. Okay, so we would say no. Then it says, does the molecule contain a proper rotation axis? Like any rotation axis? Yeah, we identified the C3, so yes. So we're now in this big one here that confuses people. This is what separates the D groups from the C groups. You'll notice at the end result. Over on the right, we have all the Ds, D3 or D3H or D3D. And then going down, we would have C3H, C3V, S6, I guess, or C3. So those are our options. We've narrowed it down to, looks like 7 options in terms of our point group. Okay. Look at this axis coming right out of the center of the molecule. All of the symmetry elements go right through the center of mass of the molecule. And coming out from the paper, we have a C2 axis. Because I'll just put a little dot by this hydrogen here, and it can be rotated around that and hit this hydrogen there. So those 2 hydrogens are exchangeable by a 180 degree rotation. That's a C2 axis. Okay, so if I can exchange those 2 protons, those 2 hydrogens, they're equivalent. Now, what about the others? Well, remember this molecule has a C3 rotation axis. So if I rotate the whole thing a third of the turn, I've identified another C2. There's 2 more hydrogens that could rotate, and those are different hydrogens. And if I rotated another third of a turn, I have 2 more pairs of hydrogens that can be rotated. So I found 3 C2 axes. They're 120 degrees apart. And because I have C3 symmetry on this molecule, and the top is like the bottom, When I rotate it a third of a turn, I can identify another C2. So if you were to have this molecule in front of you, you could do that. You could look at it and go, okay, this is a C2, and then you rotate the molecule a third of a turn, I've got another one. And then rotate a third of a turn, I've got another one. Okay. So the answer to this one is yes. Identify the highest order Cn, which is a C3. Are there 3 perpendicular C2s? Yes, there are in this molecule. So we go over to the right. Now, it's asking, does it have a horizontal reflection plane? The horizontal word is tied to the vertical axis, right? You got to know what is vertical and what is horizontal. And once we found that C3 axis, that's the Z axis. That's our vertical axis. So a horizontal plane is the XY plane. So we don't have to find that plane. It's defined by the Z axis. And so we just look at the molecule around its waist. That is the horizontal plane. Does the top reflect into the bottom? It does not, because it's staggered.
Right.
If it were eclipsed, it would, but it's not because it's staggered. Yeah, so this is not a D3H. If it were eclipsed, it would be D3H, because the hydrogens would be like this, and they could reflect down into each other. But I've rotated it now that the hydrogens are like that. Okay, so I've got 2 down on the bottom that would reflect up to the top and not hit anything, and I've got 1 at the top that would go down to the bottom and not hit anything. So reflect with this horizontal reflection plane. Okay, so that's the question right there. So it's no, it does not have a horizontal reflection plane. And then it says, does it have N dihedral reflection planes? So these would be reflection planes like the plane of the paper. Okay, so look at the plane of the paper and look at those hydrogens over here that are in front and behind the plane of the paper. They would reflect into each other. Yes, so that's one reflection plane. Well, I could do a C3 rotation and put these 2 hydrogens there, and they would reflect into each other, and that's a different plane. And I could do it again, and those would reflect into each other. So yes, I have 3 vertical reflection planes. Just pick any one of those CH bonds, and there'll be a reflection plane there. So it's got 3 dihedral reflection planes or vertical reflection planes. The sigma V's and the sigma D's, for our purposes, are the same. They contain the vertical, the highest order C rotation axis, the Z axis. So all the sigma V's and sigma D's contain the Z axis. The sigma H is the only unique one. The sigma H has the Z axis go straight through it. Okay. So we're looking at this one as a yes, and that means this is a D3D molecule. Now, that's a lot of work to get to the point group for that molecule. But look at that molecule, memorize it. That molecule is a perfect example of a D3D. So you don't have to use the flow chart once you've come up with representative examples of the symmetry species. So when you think of ethane, you've got a D3D ethane, which is drawn there, and then we'll draw a D3H over here. Yes. So I'll do my best, take my time. So it's, notice the wedges and dashes are how you tell the difference. So this is the wedge, and you have a dash. So I've drawn those hydrogens as close as I can, but the point is the non-wedged ones are on the same side, and it's a sigma H, right? They can reflect into each other. And then the wedged ones and dashed ones are on the same side, and they can reflect into each other. So that's a D3H. So if you know, like these 2, these are classic examples, then you don't have to go so meticulously through the flow chart. We had to go through 1, 2, 3, 4, 5, 6 decision points to get to that answer. Yes.
So for now, if we have a vertical reflection plane, you would we basically assume that it's dihedral.
Yeah, because that's what the question's asking. Yeah. Notice there's never a question whether you say, do you have a sigma V or a sigma D? Do you have a dihedral reflection plane or a vertical reflection plane? You're never asked to break those apart. The only time I've seen it be very clear is in benzene. Okay, so benzene has 6 reflection planes. 3 of them contain carbon-hydrogen bonds, and those would be sigma Vs. The other 3 break like the carbon-carbon bonds, and they're between, they don't have any atoms in them. So those would be D, sigma Ds. So that's the general rule, that sigma Vs have more atoms in those planes than sigma Ds. But you're never asked to decide between the two. But that's an example of the difference. Yeah. The main difference you're asked to determine is it a sigma H plane? Because you're asked about that on the flow chart. And the sigma H is always the horizontal axis compared to the Z axis. So XY plane is always the sigma H plane. Yeah. Even in benzene, so the whole plane of the molecule is the XY plane, and the Z axis comes out of the ring. It's the symmetry axis, the C6 axis. That was fun. But it's slow if you have to go through the flow chart, for especially all the way down to the corner like that. Yeah. So let me quiz you. What is the point group of water? Very nice, very nice. Okay, so what is the point group of O-phenanthylene? Let me draw this on the board so it'll be faster because I can move the whole arm. You don't know what O-phenanthylene is, but it's okay. You will in a second. All right, so. Okay, and there's some aromaticity in there somewhere. Okay, I've got this molecule. That's where the atoms are. There's some hydrogens. What's the point group of this molecule? Hey, who did it? Very good. How'd you know so fast?
It's the same shape as water.
Exactly. So, Jeff Foxworthy, if you think O-phenanthylene is the same as water, you might be a pea chemist. Okay. Very different molecules, but the same symmetry. So that's how you speed things up. You don't need the flow chart for this. The left is the same as the right. The front is the same as the back, but the top and bottom are different. You just kind of look at it and say, okay, I've got a reflection plane here. I've got a reflection plane front and back, and I've got a rotation axis, and that's it. Yeah. So that's C2V. So the same symmetry, A, whatever it is on our sheet, the A1, B1, and A1, A2, B1, and B2. This character table applies to both of those molecules. Now, which of these has 3 translational degrees of freedom? Water does, but does the other one? So, was that on the quiz? I mean, on homework, translational, rotational, and vibrational degrees of freedom? See people shaking their heads no? Okay. What we're gonna get? Okay. Well, both of them do. Let me just tell you what translate. There's one question on the exam about that. Okay, I thought it was already in this material. So, what do we mean by translation? That's translating through space, right? So my whole body can move in the X direction, right? It can move in the Y direction, and it can move in the Z direction, although not as far. Okay. Right? So that's it, X, Y, and Z. And translation means all my atoms are moving in the same direction, okay? If my atoms are not moving in the same direction, like my hips go in the X direction while my feet and my head go in the opposite direction, that's not translation, that's vibration. Okay. What about rotation? I can rotate around the Z-axis. Okay, I can rotate around the X-axis, and if I did a cartwheel, I could rotate around the Y-axis. Okay, and that's it. That's the only 3 ways I can rotate. So you have 3 translations, you have 3 rotations, and then everything else my body can do has to be a vibration. So vibrations are counted by difference. So how many things can my body do? Think of how many atoms I have. Yeah, so every atom can go in the X, Y, and Z direction, and I have however many atoms I have. There's three total degrees of freedom. So let me just get a new page here. So So the number of atoms, 3 times the number of atoms, that's the total degrees of freedom. Now, if all my 3 atoms here for water are going in the same direction, that's a translation. If this one's coming forward and that one's going backwards, let's say I hit them with a little stick or something, then it can spin, and oxygen is just rotating. So they can spin, that's a rotation. But if they're not rotating or translating, then it's vibration. So what we'll do is we'll subtract 3 translations. Notice that's not 3n, it's just 3 translations, X, Y, and Z. Okay, and there's 3 rotations. Okay, that's R, X, R, Y, and RZ. So this is X, Y, and Z. That's where the 3's come from. And so then the vibrations, (3n minus 6). So we find out the number of vibrations by difference. It's an ugly n. Do y'all see what I'm saying? So everything that's not a translation or a rotation is by definition a vibration. So my body can do all kinds of things, but if I'm not translating through space or spinning, then it's a vibration. And so the more atoms you have, the more ways to vibrate. Just like in your body, the more joints you have, the more ways you can vibrate. And they can couple with each other. My hands can do this in opposite or together. So that would be in phase or out of phase. And we'll get to that through this whole course. Each of those have different symmetries. Each of those have different ways to absorb light or interact with light. Okay. So which of these molecules has more vibrations? The top one. It's got more atoms. Yeah. Which of these has 3 translations? Kind of a trick question. They both do. They both have 3 translations. They both have 3 rotations. But they've got greatly different number of vibrations. Yeah. So that's, and it makes sense, right? I mean, the rings can vibrate and everything like that, whereas down here, the water, the only thing it can do is it can stretch out of phase, in phase, okay? And it can bend like that. Okay, so the angle can change or the bond length can change. And the bond lengths can change together, which would be in phase or out of phase. So does that match with the number that we have here? So we have 3 atoms here. How many vibrations? Well, 3 times 3 is 9. Minus 6 gives me 3 vibrations. And that's all you've got. You've got the symmetric stretch, the asymmetric stretch, and the angle bend.
Okay, so what exactly is the degrees of freedom? What is the n representing?
Number of atoms.
And then what is it for the
It's just that if each atom can go in 3 directions in space, then if I have multiple atoms, all of them can go 3 directions in space. So every particle in the universe has 3 degrees of freedom, but when they're coupled together with a bond, then some of those degrees of freedom are restricted. The translations, they have to move together to translate. So if they're not moving together, then they're vibrating. Yeah. So like the oxygen in this asymmetric stretch, like the oxygen wants to go that way, the hydrogens are going the other way. So since it's not translating, that's a vibration. So we do the vibrations by difference.
For the top molecule, there's 22 atoms.
This one?
Yeah.
Okay, don't forget the hydrogens. Did you count the hydrogens?
Yeah.
Okay, yeah, then that would be, then 3 times 22 is 66, minus 6, so that would be 60 vibrations. Yeah. And then we would be able, even with like a symmetric molecule like that, we would be able to identify the symmetry of all of those vibrations. They would be one of these, in the C2V, it'd be A1, A2, B1, or B2. Every one of those vibrations would fit with one of those symmetries. And we could determine if the infrared spectrum would contain one or more of those If it's really symmetric, then some of those are not infrared active, but in this case, so the infrared active ones in this table are the rows that have X, Y, or Z. But we're getting ahead of ourselves. It's not on this test, so. Let me get back to your questions, yes.
On quiz 3, numbers 9 and 10 talk about like setting up the symmetry of transition pipeline.
Yes, okay, very good question. Like this one?
Yeah.
Mm-hmm. So I put the tables next to it. So up here at number 8, what's the symmetry of Z-polarized light? You guys all should get this one right away. If you know the character table, right? You should be able to just go find Z in whatever row Z is in, and then come over to the left, it's A1. If I were to ask you about X polarized light, you find X, you come over, it's B1. It's only B1 in the C2V character table. If we were in, on your little sheet here, the C3V character table, then X and Y have parentheses around them, and they are sort of coupled together and they're E. So if it was a C3V molecule, X or Y would be E, and the Z polarized light would be A1. So coincidentally the same as C2V A1. Okay. So that's that. And then it says for the asymmetric stretch in water. Now this was from the notes showing you this asymmetric and symmetric stretches of water. So let's see, the asymmetric stretch in water goes along the y-axis, and so that would be B2, and then the ground state is A1. So what we're looking for is, this is the ground state, is A1. So in this ugly looking vibrational potential, the ground state looks like this, looks like a Gaussian. The excited state looks like this, okay. And for the asymmetric stretch in water, that's B2. And Z-polarized light, we're given here as A1. So Z-polarized light is A1. Okay, so this is not asking for Z-polarized light in this question, it's asking for the allowed one. But what I was setting this up was if we had B2 and Z and A1. So for this question, asking about Z-polarized light, then the Z would be replaced with A1. So it would be A1, A1, and B2. So let's do this one first. So we have A1 times A1 is A1. Let me erase this line. And then we have B2 times A1. Well, anything times A1 is it's returned. Like A1 is like multiplying by 1, okay? We can see that down here in this character table. I've got A1 here times B2 is going to give me B2. Okay. So I end up with B2. Okay, so I've done the little math. That's easy to do. You guys can figure out the procedure, but now I get to the bottom. What is my decision point? I'm looking at this integral over all space, and it's an integral of a function that has the symmetry B2. My question that I ask myself is that top row in the C2V character table? And it is not. So that's equal to 0 because it's not top row. So then we look at that, we would label that as equal to 0. So forbidden.
Just to make sure I understand how you were looking at the table in comparison to the question, you found that water is the C2V and the way it's positioned has that Z-axis up and down.
Yes.
Okay, so then you decided that the vibrational is on the Y?
So the asymmetric stretch, again, I kind of jumped ahead to that. That's the asymmetric stretch. And so the hydrogens are kind of going one direction and the oxygen's moving the other so that it doesn't translate like that. But can you see that the motion is left and right? And what's the left and right axis? It's Y. So I quickly went to the Y-axis and said that this stretch has to be along the Y-axis. So it has to have the symmetry of the Y-axis. because the y-axis has positive values and negative values, and if the hydrogens are moving in that direction, it's like they're moving in the positive direction and leaving the negative. So it's like going that way. There's a vector, and that vector is pointed towards the y-axis, and sometimes later it switches direction, but it's along the y-axis, and so it would have the symmetry of y. Now, what I didn't tell you is looking at all of vibrational spectroscopy, the ground state has that symmetric Gaussian shape around 0, and so it's even. So it's always A1 for the ground state for vibrational motion. It was in one of the lectures. Now that's what I'm doing is I'm answering kind of a different question. 9 is asking what's the setup for the allowed transition, if there is one. And so we could look at that and say, well, if I've got Z polarized, let's see, what's the symmetry setup of the transition dipole moment for the allowed vibrational transition for asymmetric stretch in water? So I know it has to be an A1 over here, and I know the asymmetric stretch in water has to be B2. Okay, so A1 is on the right, B2 is on the left, but what has to go in the middle has to sort of multiply by B2 and give me A1. So B2 times B2, anything times itself gives A1. So this has to be B2 for it to be allowed. And so then I come over here and I look and I see that B2 is Y polarized light. And that makes sense if my molecule starts out in the ground state vibrational motion, but if the motion is going like this along the y-axis, then light can come in along the y-axis, polarized along the y-axis, and interact with that vibration and make it vibrate faster. Okay. But again, with the vibrational stuff, it's just like 2 or 3 questions on these homeworks, but also on the exam. There's like basically this pair right here, 8 and 9. Yes?
How do you know that B2 goes on the left? Like how?
It doesn't really matter if A1 and B2 are switched. This is just the...
No, I meant like, how do you know it's B2 or not?
Oh, okay. So what I did was I understood what the asymmetric stretch was. Now on the exam, I'm not making you make this decision. Okay? I've simplified it on the exam. But for this problem, which you have some time at home to work on, for homework, is to look up this asymmetric stretch in the class notes and see that one is B2. So for the homework, you could go look it up to see what that asymmetric stretch is. Now what I did here in the front of the class was I noticed that motion goes along the y-axis. So I went to this character table and found y right here and shot straight across, and it was B2. So I know that B2 has to go right there. So that's the upper wave function. The A1 is the lower wave function for vibrational motion. And then to figure out if this is going to turn out to be even after I multiply this, I need a third function. That third function has to be light. And so Y polarized light is also B2. So I could put a B2 in the middle, and then this will end up, after I do the direct product of those pairs, as an A1 function in the bottom that's integrated over all space. A1's my top row, so it's not equal to 0. That means it's allowed.
So B2 is like a constant?
B2 is a symmetry, and lots of things can have that same symmetry. So I can have a vibration that has a symmetry. I could have light that has that symmetry. So it's a symmetry label, and we just need to know something about what we're labeling. So if we're labeling a vibration, it could be B2. If we're labeling Y polarized light, it could be B2. And when those two functions are multiplied by each other, they end up, the odds cancel out. All the negatives become positive, and we have an even function at the end. Yes?
So you knew it was depolarized light because that's the way that the asymmetrical stretch is going? So
This question left it open. It says we've got the allowed vibrational transition. So I know that the end result has to be A1 for the asymmetric stretch in water. Now, since this is a homework problem, I was expecting you to go find out what that is, find its symmetry. So you know that it's B1, B2, and you know that the ground state is A1, again, from looking it up in the notes, and then having to figure out which light do I use. I could have used X or Z, but those would not have been allowed. But when I use Y, then it is allowed. Again, hardest problem probably on this homework set, probably the hardest problem on the test is worth 3 points. Learn your point groups. Okay? We'll do this more. okay, in the future. But if you get wrapped around the axle on this and spend all your time trying to study this and don't get good with your point groups, it's going to be a bad exam. So know the symmetries, know, just the basics of Vesper shapes, like a SP2, SP hybridization, and the angles. It's really 4 options, right? SP, SP2, SP3, 3 options. And you can know that it's 180 degrees for SP, it's 120 for SP2, and 109.5 for SP3. So a little bit of review there, but that's how we get the 3D shapes. I'll put a couple of those problems on there. So that's 6 points. Okay, so again, not a huge part of the test, but enough for you to get some points on it. And then the rest is like point groups, and there's like the classical physics, there's like 3 questions on there with like is it the UV catastrophe, is it the photoelectric effect, is it the black body radiation or atomic line spectra. So just quickly review that first homework set, because I asked you some questions on homework 1 about those classical physics failures. So don't let that catch you off guard, because that's way back in homework 1. I think you're more prepared than you think. Be confident. Okay, yes. No, so we're going to do a calculus lab, and that'll be all of the calculus substitutions and stuff like that. And so that'll be on the next exam.
Did anyone bring up how apparently that was due 2 days ago?
No, we're working on it. So send me, if you've noticed something like that, send it to me and I'll fix it. Yes, I swapped those labs, so the due dates might be screwed up.
I remember you saying that you have a 3x5 note card. Is it
Yes.
front and back?
Yes, it is handwritten though. I don't want to mass produce like one smart person make it and pass it out, sell them for 50 cents.
So I was watching the video lecture.
Yeah.
And it kind of like had talked about I can't see like the PowerPoint fill in blank. It just
Oh,
says
okay.
otters.
Oh, okay. All the like if it wasn't last year's lecture that you can see, maybe the year before on YouTube. So look there first. If I find one that has it, then I'll send it to you.
And do we need the blue scan card or can we use the green one?
The color doesn't matter. It just needs to be the 50 question long one. Yeah.
What's the importance of the square in this problem, in the answers in the second one? Because you didn't write them on the first one. so-
Intensity is related to the square of that integral, so it's really just more accurate to have the square.
Okay, just cut off around.
Yeah. Whether it's the real important thing is whether it's 0 or not. But good observation.
Thank you.
Uh-oh. Did it break?